Today, Anthropic has officially launched its next generation of artificial intelligence, debuting a powerful new tier called the Mythos class. This class is designed to sit above the previous Opus models, establishing a new performance baseline for the company's generally available systems. But the central detail of this release is a paradox. Claude Fable 5 and Claude Mythos 5 are not distinct creations. Both products run on the exact same underlying neural network. They share identical weights, training data, and core intelligence. The difference lies in how that central core is encased and deployed to different user groups. This bifurcated architecture exists because the raw intelligence of the base model has crossed a critical threshold regarding dual-use applications. In its unconstrained state, the model demonstrates high proficiency in autonomous network hacking and the rapid design of biological pathogens. Because of these risks, granting raw API access to the underlying weights is now categorized as a dangerous deployment strategy. We are going to deconstruct the specific capabilities that trigger these concerns and examine the routing architecture Anthropic designed to contain them. Today, safely releasing a frontier AI has moved far beyond simple text filters. It has become a massive, high-stakes systems engineering challenge. To understand the threat, we first have to look at the primary capability shift of the Mythos class, the transition from single-turn text generation to long-horizon autonomous execution. The clearest evidence of this autonomy appears in software engineering. During early testing with Stripe, the model was given a massive refactoring objective. This chart compares execution timelines. The AI agent performed a code-base-wide migration on a 50 million-line Ruby code base in a single day. Historically, that specific task would require an entire team of human engineers working by hand for over 2 months. This autonomy extends to native vision processing. The model interprets visual data without relying on external developer tools or structural scaffolding. In the Pokémon Fire Red benchmark, the model successfully completed the game using only raw pixel input from the screen. It navigated the environment and made strategic decisions without any access to underlying game state data, internal code maps, or structural navigation aids. The third major upgrade driving this autonomy is long context memory optimization for persistent multi-step tasks. Anthropic tested this memory capability by deploying the model into the deck-building game Slay the Spire. By granting the model access to persistent file-based memory, it actively took notes and improved its own strategy over millions of generated tokens. These models function as autonomous digital workers, capable of sustained execution over extended timeframes. When this level of unassisted execution is applied to malicious goals, we measure the risk in terms of uplift, the specific advantage an AI provides to a threat actor. The first major threat factor is biological research, specifically the model's ability to generate novel, compelling scientific hypotheses. The primary evidence for this risk comes from a benchmark task predicting the viral shell assembly of adeno-associated viruses, or AAVs. This scatter plot compares viral shell assembly prediction accuracy. The general-purpose Mythos class model emerges as a massive outlier, outperforming sophisticated, dedicated protein language models, despite having no explicit biological training. This exposes a dual-use reality. The exact same biological reasoning required to design delivery systems for gene therapies can be inverted by a malicious actor to design dangerous viral pathogens. The same pattern emerges in cybersecurity. Here, the risk moves beyond simply writing malicious code and scales into offensive operations. There is a vast difference between asking a model to draft an exploit script and instructing it to execute agentic hacking, which involves live network reconnaissance, rapid target discovery, and lateral movement. This bar chart tracks cyber evaluation success rates from Anthropic's internal red teaming. It shows that when the unrestricted base weights are deployed, the model achieves near total success on complex offensive cyber tasks. Combining long-horizon autonomy with native structural logic makes the raw model an effective tool for cyber attacks. Because these tasks are inherently complex and dual-use, traditional alignment, simply instructing a model to refuse bad requests, fails to address the underlying risk. Rigid refusals within the model create their own problems. They disrupt legitimate technical research and remain vulnerable to jailbreak attempts. Anthropic's solution to this engineering problem is the Fable 5 deployment architecture. Fable 5 operates as a system wrapped in distinct, separate AI safety classifier nodes. This architecture intercepts every user prompt via a central safety classifier node before reaching the main weights, scanning for cybersecurity, biological research, or model distillation queries. The path branches, a green path leading to the Fable 5 base model, and a red path routing away. If a query is flagged, the system dynamically routes the prompt to a highly capable legacy model, Opus 48. This preserves the user experience while mitigating risk. In practice, more than 95% of Fable sessions use the frontier model without ever triggering the fallback routing. The security efficacy of these isolated classifiers is stringent. Over 1,000 hours of external bug bounty testing yielded 0 universal jailbreaks. To protect the weights from advanced evasion, Anthropic instituted a final security layer, a mandatory 30-day data retention policy for all traffic on Mythos class models. This data is retained specifically to detect slow, persistent, multi-turn attacks operating across hundreds of separate distributed queries. This monitoring mechanism directly targets well-resourced state-level actors attempting capability distillation. In this architecture, AI safety functions as a distributed dynamic network of defensive routing checkpoints. This architecture enables the two-tiered deployment strategy that defines this generation of frontier models. This matrix compares the two deployments. On one side is Claude Methods 5. This provides raw, unconstrained capability, but it is deployed exclusively through Project Glasswing to vetted cyber defenders and life science researchers. On the other side is Claude Fable 5. This is the commercial product constrained by classifiers yet retaining state-of-the-art capabilities for standard enterprise software and complex analytics. Despite these different access paradigms and safety profiles, the core intelligence driving both systems remains identical. This bifurcated launch indicates a transition for the artificial intelligence industry as a whole. As frontier models scale their logical capabilities, the focus of engineering must shift. Developers must now build robust deployment wrappers alongside the training of the models themselves. These wrappers must parse human intent, separating legitimate utility from malicious uplift before ever allowing access to the raw machine intelligence. The trajectory of artificial intelligence now depends on the precision of its architectural containment.